Thanks, Sandip, and thanks for the invitation to speak. I'll make sure to write big. If you can't see something, just let me know, and I'll make sure to write bigger. So yeah, thanks for the invitation to speak and invitation to be at this exciting conference. Too bad I was sick for most of it. So today I will tell you about an idea connecting TTbar and the black hole interior based on work in progress with my postdoc Simon Lin and my graduate student Shadi Ali Ahmed. So TTbar is somewhat of an old subject, and while I didn't get into it during its peak, I decided to finally go back. I had some free time, I guess. I decided to go back and learn the subject and see if there was something that was missed. In fact, Joe talks about this strategy in his memoir, where he would wait until the sort of a topic sort of died down, and then he would go back and look for gems. And Joe being Joe, he often finds them. So I thought, might as well try to emulate him. But obviously, I can replicate the process. I'm not sure I can replicate the results. Okay. Anyways, so let me begin by reviewing a major problem or a hurdle towards understanding the black hole interior. So ADS-CFT has been great, and it taught us a lot about black holes, but mostly from the outside, and not a whole lot about the inside. What it does tell us about the inside are often sort of extensions or continuations from the outside. What is missing are interior operators that are non-perturbatively defined, let's say, either intrinsically in the theory of quantum gravity or from the boundary perspective. Okay, embarrassingly, the only operators in ADS-CFT that are well-defined non-perturbatively are those near the boundary. And the dictionary for those operators just goes by the name of the extrapolate dictionary. Extrapolate dictionary. Namely that the boundary limit of bulk fields goes to local operators on the boundary. And that's it. Okay? The issue with trying to start from this and then trying to make something definite about the interior is that there's this enormous gap between them. And the reason why this is a problem is because we don't have control over what gravity wants to do in the intervening space. You can fix boundary conditions here, but then gravity can do whatever it wants. You sum up over, let's say the gravity path integral would sum up over states where you actually have the black hole that you wanted to probe. But then there are also states that don't have the black hole. So how do you make sense of this operator that you're trying to define? So, these papers that talk about probing the black hole interior, for example, the paper that Adam Levine was talking about the other day, really they should come with sort of a warning label, like the warning you see just before you enter a train. Mind the gap. Okay. Now, since it's the boundary where we understand things better, so it seems natural to ask if there's a way to place the boundary inside the interior, so that the interior operators, given that they're now at the boundary, have a more well-defined definition on the boundary, at least holographically on the boundary side. A first step towards shrinking the gap between the boundary and the interior, or and the black hole, was proposed by McGuff, Meze, and Verlinde, who said that if you start with a holographic CFD and construct a family of TTbar deformed theories a la Zamolodchikov and Smirnov, so you define a set of theories via this flow equation, holographic QFD, that's what this stands for, integral d squared x TT bar. So this is Zamolodchikov and Smirnov. That's this definition. They said if you define such, if you consider applying this for holographic CFDs, the parameter lambda, which labels the family of QFDs generated by this flow, has the bulk dual of moving, or rather of being related to the radial direction of where the holographic boundary is. Let me draw that for you. So for example, the boundary can be pushed to some location there. So the boundary here is at r equals infinity. This is the asymptotic boundary. I'm imagining that my r is some radial direction. The radial location of the boundary in this TT-bar deformed case goes as a function of lambda. It goes as an inverse power of lambda. So,
Ahmed, is this best defined in the Euclidean case, or do we think it works equally well in the Lorentzian case?
My understanding is that there's no difference.
Okay, thanks. Yeah. I mean, the reason I was worried was that you could think of this in the bulk as some radial Wheeler-DeWitt equation. I mean, the TT-bar deformation, which is kind of best defined in the Euclidean setting, but okay, maybe you're saying you should think of it working as well in Lorentzian.
Yeah, I don't see what the problem. Why can't you just continue whatever solution you have?
Yeah. Okay. I mean, it might just be subtle for the black hole, but sure, please go on. Yeah.
Okay. Are you worried about the complexification?
Yeah, I'm worried about the fact that if you did this, for instance, in the cigar geometry, it might work very well, but then you wouldn't see the interior, precisely because I guess the objective is to see the interior.
Yeah, I'm going to get to that.
Okay. Thanks.
Sorry.
Yeah, my worry is about the complexification. I don't think this makes any sense for the sign that you want to apply for going into the bulk.
Yeah, let me get to that. Okay. So I will get to that. So first of all, what McGuff, Meze, and Verlinde show so far is that if you consider this class of this family of field theories, you can relate the radial location of the boundary to this parameter lambda, and it seems like for them you can only go up to the horizon. Okay? There's a critical value of lambda where lambda goes to 0 as the boundary, and as you increase lambda, you get closer and closer to the horizon, and things break down once you try to go through the horizon. But I'm going to give a modified prescription, which I claim can push the boundary into the interior. Right? Yes?
No, this was. So I thought what happened was that beyond a critical value, you started getting these complex energies, and that was when you were in the interior. Are you saying that?
I'm saying that that's not true. So when you get complex energies, you're not actually in the interior.
I see.
Okay, so we are getting a bit ahead of ourselves. So, okay, that's where I'm going. I'm going to give a modified prescription that gets you the orange line. That's the motivation, and here's the outline for the talk. I will start on the boundary. I will review the standard TTbar story, then give a slight modification to generalize it to the case where you have multiple different flows. After we get the results for that case, I will talk about the bulk, provide a gravity path integral with certain boundary conditions that implement what I will do on the boundary. And I'll give you what the boundary conditions need to be that give you a gravity path integral for the interior. Okay. So let's start. Let me just write TTbar. Okay. So the subject of TTbar starts, well, with the TTbar operator. What we mean by TTbar is that it's, as an operator, it's the determinant of the stress tensor, determinant TAB, which is given by this in holomorphic coordinates, T times T bar minus theta squared. Theta is the trace, and this is a nice combination. This is a nice operator constructed of constructed of the stress tensor because it is Lorentz invariant. Okay, the reason why this is an interesting, another reason why this is the reason why this is an interesting operator is that it has this very cool property that it factorizes, as shown by Zamolodchikov. And if you compute its expectation value in a primary state, it is given by the following expression. Okay? Yeah, it's expectation value of this object. Yes, yes, yes. Thank you, yes. Expectation value of quotes TTbar, yes. This is exact. Yes.
Point splitting. It's well defined by point splitting.
Yes.
It's well defined. The operator is well defined by point splitting. It doesn't have divergence. It's a nice double case.
Yeah. Okay. Then Zamolodchikov and Smirnov showed that you can define a TT-bar deformed partition function. Oh, there are too many z's here. Through the equation d lambda log z lambda is equal to, I'm putting tildes because I don't want to keep track of the numerical factors, dx expectation value TT bar in quotes at lambda. Okay, maybe I'll just do this. Okay, so they showed that this thing can be solved provided that you put the boundary condition that z at lambda equals 0 is the partition function of a conformal field theory. This boundary condition is very important to actually be able to solve this equation or to solve for the theory. The reason why you can, well, the way that you go about solving this theory is to note that this equation actually implies two equations on the stress energy tensor. The first you obtain by applying the variation with respect to the metric on both sides, which will give you derivative of lambda. Well, when you act with this variation on the left-hand side, you bring down a factor of the stress energy tensor. And when you apply to the right-hand side, you'll just get the background metric, gamma AB, times TTbar. I'm going to stop writing quotes. There should be quotes around that. Note that I'm eventually going to take this gamma AB to be the flat metric. All right, so this is one equation. The other equation is to note that since lambda is the only scale in the problem, taking a derivative with respect to lambda is like implementing an infinitesimal scaling transformation. So this is like dd lambda is like variation with respect to the conformal mode of the metric, and so you would get. So I'm going to write d lambda. You would get the trace of the stress tensor on the left-hand side. It's going to be divided by lambda. And now it's just equal to the right-hand side, t bar lambda. Okay? So you get these two separate equations.
The right-hand side of your first equation, the right-hand side, when you take that derivative, why don't you also get 3-point functions of the stress tensor? Because you have a two-point function that's integrated, and that is an expectation value. So when that hits the there should be some 3-point function, no?
Let me think. Okay. The way that I was thinking about it was that here, so the right-hand side on a general metric, on a general background, has a factor of the square root of gamma here. And I was imagining that it was acting just on this factor. Now, yeah, but now I'm confused about why doesn't it act here? I'm sure there's a reason why it doesn't. Let me get back to you on that. Unless maybe somebody has the answer to that question.
I guess one can argue that in large N limit that will drop out.
No. This is independent of the metric, but this expectation value here, this is like the partition function of this involves the background metric that the CFT is living on, or that the QFT is living on. So why doesn't the derivative act on that? There should be. Okay, I'm blanking out on this.
Ahmed, I thought you could just decouple the TTbar by going to a background, integrating or random matrix in the background as Cardi did.
I don't see how that addresses this.
No, but then the couplings are all linear. Then there's just some HABT and HAB bar T bar. There's no.
Okay, let's come back to that later. I think it's better. Okay. Anyways, so if you take those two equations and then you consider applying them to the case where the state is a primary state, and you look at the TTT component of the stress tensor, you get the following differential equation for TTT, which is just the energy. Okay. Whose solution, so this is a first order differential equation. You need just one boundary condition. If you plug in an initial energy, a seed energy E naught, then you find a solution that just grows like this, and it has the following form. E, or let me just write 1 over 4 lambda, 1 minus square root, 1 minus 8 E naught lambda plus J squared. There's some factors I'm ignoring. Okay, and the reason why I stopped evolving here is that, and there's a lambda squared here actually. The angular momentum. So I'm looking at a primary state that's labeled by E and J. For large enough lambda, the argument of the square root goes negative, and so the energy complexifies. So at some point here, you go off in the complex plane. So that's how it works. And what I'm going to do now is give you a prescription to avoid this complexification. Let me first state that the critical value of lambda depends on the energy. Okay? So for now, let's just set J to 0. The critical value of lambda is 1 over 8 times the seed energy E naught. So if you pick an E naught, or rather for any value of lambda, there will always be some energies that have complexified and some energies that have not. Okay, that's one comment I need to make. Now let me give you the prescription to avoid this complexification. And because different energies complexify different lambdas, I can only achieve this for a particular energy. I first have to make a choice. So my prescription will be the following. So for lambda greater than lambda c, I will first pick a preferred E naught. Okay, my J is equal to 0. 2, in this case, lambda, the critical lambda is just 1 over 8 E naught, as we just said. 3, the important point, or the new step, is I'm going to add to the action a cosmological constant term. So I'm going to take rather I'm going to add to the deformation TTbar to TTbar plus 1 over lambda squared. So it is a lambda-dependent cosmological constant term, which modifies these equations. Now, so it modifies this here by adding plus 1 over lambda squared. And similarly, here and here. Okay. This also modifies a differential equation by adding 1 over lambda squared here. Let me set J to 0. Okay, then you can solve this, and the solution of this equation the general solution is E lambda equals 1 over 4 lambda 1 plus minus square root lambda times some integration constant minus 1. Okay, so this is the general solution of this differential equation.
Sorry, just a question.
Yes.
Should we think about this deformation on the right-hand side as Hamiltonian divided by gamma? I mean, I'm just trying to check if this is state dependent or if this is something you can write in a state independent way, this particular deformation, the one where you added the extra term, because it seems to depend
as written, this is theory independent. Okay?
But also state independent, because you added E1 by gamma into E naught, right?
Yes, yes. So this deformation is state and theory independent. The prescription I'm going to give you is state dependent.
Okay.
Yeah. Exactly. So this appears in the prescription. So okay, so let me say it a bit more slowly. So suppose we fix a seed energy E naught. We notice that if I keep flowing E naught, at some point it's going to become complex. Now I'm going to give you a prescription that allows you to continue to evolve E naught in a non-complex way. Okay? So that keeps the energy real. I don't make any guarantees about what it does for the other energies. I just care about E naught. In that sense, it is state dependent.
No, but can't you just write this term as the integral of T, which will just pick out E naught when it acts on E naught, and if it's a different state, it'll pick out the energy of that state?
You mean
I mean, there's some operator that picks out the energy eigenvalue. Can't we think of this as just adding that additional operator apart from the TTbar?
No, I don't think I don't think you can think. The thing is, I don't want to add a different operator to the action, because then I don't know if I can solve it.
Okay.
The nice thing about just doing this is that we know how to solve this theory, a la Zamolodchikov and Smirnov.
Okay. Okay.
Do something more complicated, then I don't know what to do. Yes? Well, good. So what fixes C and this plus or minus? That's the question. The way I want to fix it is that I want to impose continuity for all the energies, independent of whether they become complex or not. I'm going to take this prescription and I'm going to apply it to all seed energies. But note that I'm fixing E naught. There's an E naught in the prescription, and then there's the seed energy that you apply it to. But it's a fixed lambda C. Yeah. So we can talk about the other energies later. For now, let's just focus about what happens to E naught. Yeah.
I'm confused by this. I thought the theory is defined by starting with a conformal field theory, deforming by the TTbar operator, but then you define the operator at every lambda step independently after the RG flow. Now, what you want to say is you take an equation for some observable and deform that, but that doesn't define a theory. That just defines some observable that you've come up some prescription for. But I would have thought the right thing to do is to do what Suvrat wanted to do, which is to put this in the action.
This is in the action.
No. I mean, then what do I do when I start at lambda equals 0? Let's say I start in the conformal field theory. What are you deforming?
No. So yes, it's in the action with a theta function, roughly speaking.
With what operator? Identity?
Oh, yeah, this is the identity. Yeah, exactly, the identity.
The identity in the original CST and appropriately deformed to whatever it happens to be as you flow?
I think the identity doesn't change.
Why? It's not a local theory at any lambda. But the theory is not nicely defined, right? Is there a local operator for for any given lambda?
I am adding the cosmological constant, but I think Mukund is asking, what is the cosmological constant proportional to as an operator? Like the cosmological constant as an operator, is it the identity operator times something? I think yes. That's right. Yeah. Yeah, I don't know what. Okay. I mean, there is a sense in which lambda is like a cutoff. One way to see that is this point that for any fixed value of lambda, there's a highest energy beyond which all these energies complexify. So in that sense, you can maybe think of it as a cutoff. You should not consider higher energies than that, than 1 over lambda. Yeah. Okay. So if you take that expression and then fix the integration constant along with the branch of the square root to get continuity for all energies, you get, thank you, you get a flow which looks like this. It basically just takes the inside of the square root and it just multiplies it by a minus sign. Okay, so that's the effect of that deformation. Let me just a quick comment. Something like this of adding a cosmological constant term to change the flow has been considered by other people, including Eva Silverstein and Ronak, amongst others. Okay, so that's from the boundary perspective. And just as I was focusing on a particular energy level, I'm going to do something similar now on the bulk side. The question is going to be, what is the gravity path integral way of implementing what I just did on the boundary? Yeah.
Gave the effect of the change of sign of this term in the square root. You had the C over there, right? So I couldn't really follow how that led to this.
Oh, I don't have a quick argument. It's just it has some differential equation and you have to solve it.
All right.
Yeah. Okay, so on the boundary,
you picked that C because you wanted the curve to be continuous.
yes.
So that was your definition of the, I think that was the
Oh,
question.
was that the question? Oh, maybe I misunderstood. Yes. So as I said, the general solution has this sign choice and the value of C. By requiring that all the energy levels are continuous throughout this two-step flow, fixes both. It fixes C to be 8 times E because they have to agree here, and also the sign. Yeah. Okay. No, you see, you cannot plug in lambda equals 0 in this. Right? This is only valid for lambda greater than lambda C. Yeah. Yes. No, at the same value of lambda critical. Yes. Correct, correct, correct. Thank you for asking. That's important. Just actually, yeah, that's important to fix this, to fix this sign choice here. Because if you only look at E naught, you can't fix this sign choice because the square root is 0 at the interface. That where you change. Anyways, so on the boundary we had two inputs. There was E naught and lambda. The question is, what do those correspond to in the bulk? Okay. I'm going to analyze this in the setting of JT gravity as viewed as embedded in 3D Einstein-Hilbert plus cosmological constant. So Einstein, Hilbert plus CC. I'm going to restrict my analysis to just pure gravity. This means I only have the metric G and the dilaton phi. And the way you embed JT inside three-dimensional gravity is to write down the metric, three-dimensional metric, as 2 dimensions squared, and the dilaton plays the role of the radius or the circumference of the transverse dimension. Okay. Yes.
So lambda is a perturbation parameter, and you imagine it like changing the perturbation parameter continuously, right? In the CFT at least. That's the right way to think about it.
Yeah, so you start with lambda equals, so you have some flow equation, and the initial condition is the theory where lambda equals 0, and then you gradually increase lambda. And the theory changes and adapts as you do that.
Yeah. Yeah, at least in QM, like what we do in quantum mechanics and perturbation theory, like if your del E by del lambda is not continuous, you have to do some infinite wave function renormalization. Isn't that right? Like.
Okay.
So I'm just trying to understand, like, though your energy is continuous, since there's a kink, is that an okay thing to do? Like.
Yes, so in both phases of the flow, before lambda critical and after lambda critical, purely from the definitions of the deformation, you can derive 2 independent flow equations. Both are true exactly on both sides. Then there's a question of just joining them, and we just join them by just boundary conditions.
But don't you have to match the wave function renormalization if I was doing it at QM, like naively?
I think this is all taken into account by the fact that the deformation has all these special properties. That's my understanding. Okay. So where was I? So, okay. So we want to match to some notion of energy on the boundary. So it's good to review different notions of energy, or rather study different notions of energy in the bulk. The first notion of energy, bulk energy. Yes? I will get to E naught in a second. So right now, I'm going to consider a general spacetime. Then I'm going to give you ultimately the boundary conditions that fix what the bulk dual of E naught is. Yeah. Ultimately, I care just about E naught. Okay. The first notion of energy is going to be something called the Hawking mass. Okay, I'm going to label as M. This is it's a quantity you can write down that, at least in my understanding, has nice properties and makes sense really only for spherically symmetric situations. I was happy to see that this was recently discussed in a paper by Ronak and Aaron. It came up in their this new bound that they wrote, and I think Ronak mentioned it at the end of his talk. So I'm going to assume spherical symmetry from the high dimensional perspective, which just amounts to saying that I'm doing JT gravity. Okay. this Hawking mass has a special property that is actually, it's a constant in your space-time. Am I out of time? Yikes. Okay.
Move 5 minutes.
Okay, thanks. Okay. Let me tell you how to define this Hawking mass in the context of JT gravity. In fact, you can extract it from the constraints of JT gravity when working in the ADM formalism. So suppose you slice your space-time in some way like this. You can take there's a linear combination of the constraints of the Hamiltonian plus the diffeomorphism constraints with metrics and extrinsic curvatures multiplying them. You can take this linear combination and you get something that looks like dr times phi squared minus d mu phi d mu phi. Okay? Because the constraints vanish, this tells you that the quantity inside here is constant along any of these Cauchy slices. Okay? This I'm defining, this is what I mean by M. Okay? Note that this thing is essentially what Ronak had. So you have the area plus the derivative of the area in the two orthogonal directions. Okay. The second notion of energy is going to be the quasi-local energy. Oh, I should have mentioned that this M turns out to be just equal to the ADM mass. By definition, yes. No, as M is a constant of, it's a constant, it doesn't depend on R. It is just equal to the ADM mass. Yes, it agrees with the ADM mass, yes. In the spherically symmetric situations, yes. The second notion is the quasi-local energy, or the Brown-York energy. And it has the usual definition, minus 2 over gamma d by d gamma tt of your action. Okay? And in JT gravity, this is just equal to the following: E Brown-York gamma tt phi minus d dn tilde phi. Okay. What I mean by dn tilde phi is you have your boundary at constant r. I guess I should have said that. I'm assuming my boundary is at constant r, at fixed r. And tilde is the normal to the boundary. Okay. This energy here, gamma is the induced metric on this boundary. Metric here. And yes, thank you. This energy is because it's a derivative with respect to the induced metric. It's actually still a bulk energy. You need to renormalize it to get a boundary energy. I'm going to skip the steps for doing that, and just believe me that it's going to be equal to phi squared minus phi dn tilde phi when you renormalize. And if you take this and you plug it into well, the observation here is that the M and EB, because they are expressed in terms of the same quantities, you can express if you express them in terms of one another, you get that the E Brown-York is equal to phi squared 1 minus square root 1 minus m phi to the minus 2, which is essentially the TTbar form for the energy. Okay. I'll be done in a minute. Let me write out the form of this of the mass. This is phi squared minus d n tilde phi squared. All right, I am getting ahead of myself. Sorry. Let me at least just give you the punchlines. What we showed after having written down or expressed the energies in the TTbar form, this fixes what E naught and lambda are from the bulk. It's m and phi to the minus 2. Now the next step was going to be to define a gravity path integral with boundary conditions of fixed m and phi squared. Let's look at this expression for m. I'm going to define a path integral with m and phi squared as boundary conditions. But look at this relation between m and phi squared. There's something funny about it. As you take phi squared smaller and smaller and smaller, at some point m will become complex, because this tells you that there's a minimum value for phi. Okay. I just mean that because this thing is a purely negative number, if you make phi squared small enough, there won't be a solution unless you set this thing to be, unless you allow the derivative to be imaginary. Okay. This phenomenon is the same as the phenomenon of the energy complexifying on the boundary. But notice that we made an implicit assumption here. This relation is only true when you assume that the normal to the boundary is space-like. If you relax that assumption and allow the normal to the boundary to become time-like, that actually changes the sign that's inside in the definition of the Hawking mass. But if the normal of the boundary is time-like, then you are actually in this region, inside the black hole. So this would be like the boundary is at a constant R slice, but a constant R slice inside the interior. And the normal is time-like. And the thing that I was going to show was that if you apply the Brown-York energy prescription to these slices, you get exactly this modified spectrum, but where you just flip the sign of the argument of the square root, and it is still real, and you get this flow. The stuff that's the main punchline. The other punchline I was going to talk about is how to read off from the behavior of this energy flow, basically what happens as you make lambda as big as you can, connecting that to the location of the singularity in the interior. But let me stop here. Thank you.
Thank you, Ahmed. So we are out of time. We can set up the next talk, and maybe within that time we can have a question.
Pratik? Oh.
Yeah, so to repeat, to get the flip inside the square root, you need to change the precise definition of Brown-York stress energy across the horizon, putting an I somewhere.
No. So what we found is that the definition of like this definition stays the same, But the only thing you need to take into account that because the normal of the boundary is time-like, the sign of the Brown-York term is flipped has a flip and a minus sign. That is true independent of what I was trying to do. That's true just from applying Stokes' theorem in the setting of having a time-like boundary.
Okay, so yes.
Sorry, space-like boundary.
Yeah, so you're saying that this flip is actually natural from some bulk point of view?
Yes, it is natural from the bulk perspective.
That's exactly what I was asking, thanks.
No. The theory is still the same. Everything about TTbar, etc., that just comes into the boundary conditions for your bulk theory. I think Parrikar had a question a long time.
Was it an M squared? This looks like it has a real solution, right? Like I didn't see what. Oh.
M and phi are real.
Uh-huh.
If you take phi to be small enough, the only way that can happen is if d and phi is imaginary.
I see, that's what you
Sorry, I was rushing. And, yeah.
All right, let's thank Ahmed again.